Okay, in this lecture, we'll focus on task 1. So it's Chern-Simons partition function, and now it's in 3-manifold. So for this moment, I want to invite you to forget about 4D for a moment, and we will only focus on 3D in this lecture. And also give you an alert, and the content I'm going to introduce to you might not be very familiar to people in the LQG community, so I will try to go slow. And it's hard to deliver the full detail, but I will try to deliver the idea. And some details I will refer to the lecture note, which you can find from the website. So let's get started. And the first thing we discussed is the Chern-Simons partition function on an ideal tetrahedron. And what is the ideal tetrahedron? Let me first give you a definition. An ideal tetrahedron, I will denote it by a triangle, and it's a tetrahedron whose vertices are located at infinity. And so to represent that, I would represent it by some vertex truncated. I would represent it by truncating vertices. So at the beginning, I have a tetrahedron like this. To represent that they are at infinity, I would just truncate the vertices. So I will get something like this. I will become a triangle. This is a triangle. And these are the truncated vertices. So you can just understand the ideal tetrahedron as some vertex truncated tetrahedron. Okay? And on the boundary of this ideal tetrahedron, there are two kinds of boundary. And the first kind is the original boundary. Now it becomes a hexagon, for example, this one. And we classify it as the geodesic boundary. Just a name. And the second kind is created by removing the vertices. And for example, this one, this triangle created. And this kind of boundary, we call it a cusp boundary. And we do this because we want to use a technique called ideal triangulation. And it's a way of discretization. Triangulation is a way to discretize a 3-manifold, a graph complement 3-manifold. And what is ideal triangulation? It's basically that if I can decompose it into a collection of several ideal tetrahedra, then this is the ideal triangulation of a graph complement 3-manifold. But it's triangulation, but I want to give you, just to clarify that an ideal triangulation is not the same as triangulation. So because first of all, when we talk about a triangulation, usually we talk about triangulation of 4-manifold if we study 4D quantum gravity. And the ideal triangulation, we usually consider it for a 3-manifold with a boundary. So its boundary is not an empty set. And also, it's also not the same as the triangulation of a 3-manifold. It's a very different construction, just to clarify that. So don't try to connect it with a triangulation. Now, in our example, we want to do the ideal triangulation of our 3-manifold, which is the gamma-5 graph complement of a 3-sphere. And it's hard to tell you how to get the result, but let me just tell you the result. The ideal triangulation of this 3-manifold is a collection of several ideal tetrahedra, and the result is that it can be decomposed into 20 ideal tetrahedra. And to see the whole picture, I will just refer you to the figure 4 in the lecture note that I provided. And just to give you one hint, which is that the boundary of this ideal tetrahedra, which is this cusp boundary, they are located on the annuli. All the cusp boundaries are on the annuli of the graph complement, the gamma phi graph complement of the 3-sphere. And so for now, I just want you to accept this fact. The ideal triangulation of this 3-manifold gives you 20 ideal tetrahedra, okay? And recall that, what was our goal for this task 1? Our goal is to construct the Chern-Simons partition function on the gamma 5 graph complement of 3-sphere. And why do we do this ideal triangulation? It's because the partition function on the ideal tetrahedron is known. Then to construct the partition function for the whole 3-manifold, then it will basically becomes a product of 20 partition function, each on one ideal tetrahedron, and upon some constraint imposed. So I have several constraints, and that's it. So it's very simple. And so our task 1.1 is to construct this partition function on a ideal tetrahedron. So let's do that. So the main thing in this lecture is to explain how we construct it. So we start from classical setting. First, we consider the Chern-Simons phase space for the boundary of an ideal tetrahedron. So first consider a general 2-manifold. I will denote by sigma. And the phase space of Chern-Simons phase space on a 2-manifold is the phase space of Chern-Simons theory, whose gauge group is, say, G, on this 2-manifold, is defined as the moduli space of flat connection. So moduli space of G value flat connection on this 2-manifold, and it's defined as the flat Lie algebra G value connection on this 2-manifold quotient by the G action. And this is proved that it's isomorphic to the homomorphism of a fundamental group of this 2-manifold to the G group quotient by the G. And this basically that you can understand this homomorphic as the holonomy, which is a representation of the fundamental group. And this quotient is by the quotient out of the gauge. Let me give you an example, which is actually a very important example. We will use it tomorrow. And the example is consider the 2-manifold to be a 4-sphere. Now I have a 2-sphere and remove 4 points. There are 4 holes. And the fundamental group is generated by 4 loops located starting and ending at the same point. Say this point, I have 1, 2, 3, 4, each surrounding a hole. And I'll call it L1, L2, L3, L4. And the fundamental group is generated by these loops, and they should satisfy the condition that combining all these loops together, it gives me 1. And here, this Li, they are in the fundamental group of the 4-sphere. And this homomorphism is just to write the holonomies that are along this loop, and this holonomy takes the value in the G group, and this condition can be written as a closure condition. So H4, H3, H2, H1 equals to identity in the group G. And this quotient is by gauge, so we know that, so the gauge is HI goes to G, HI G inverse for any G in this gauge group. And this is nothing but changing the base point. Here, this base point to define all the H. If I change the gauge, the base point to another point, that is the gauge transformation. Okay, now this is just an example to explain what is the moduli space of flat connection. Now, our two manifold is the boundary of the three sphere. Then the moduli space is the moduli space of G value flat connection on the boundary of a three manifold. I would denote it by P partial M3, partial M3. And let me also tell you that this manifold, in general, it's a Poisson manifold. And the boundary of a three manifold is a closed manifold, and this becomes a symplectic manifold. So it has symplectic structure. And on this phase space, because we study the Chern-Simons theory on the three manifold, and that the boundary is, so the flat connection means that the curvature of the connection is flat. But that the boundary of a three manifold is flat doesn't mean that the bulk is also flat. And if I require the bulk is flat on this three manifold, then I will get a sub-manifold of this phase space, of this symplectic manifold. And this is actually a Lagrangian submanifold. I will denote it by LM3, and it is a Lagrangian submanifold of this symplectic space or phase space of Chern-Simons theory on the boundary of a three sphere. What is a Lagrangian submanifold? Let me give you the definition first. A Lagrangian submanifold, say L, of a symplectic manifold which I call M. It's a symplectic manifold, so it also has symplectic structure. It's such that, so it's a submanifold of this symplectic manifold such that the symplectic form, if I restrict it to this submanifold, it gives us 0. And also, the dimension of this submanifold equals to 1/2 of the original symplectic, of the 1/2 of the dimension of the original symplectic manifold. And this is not something that is very new. We actually have a very easy example of it. An example is I consider M is R2, and the symplectic form is dp wedge dx. And then I define our symplectic submanifold to be L equals to, like I let the L is constructed by let P equals to 0. Then the L itself is isomorphic to just a real line. This, we do it all the time. It's nothing but to choose X as the polarization. And then we do the canonical quantization. Then we construct some wave function which is a function of the position X. And then the P becomes a derivative operator. So we've seen that. And now the Lagrangian submanifold we are interested in, just a generalization of this concept. Okay, now, this is just to give you some general definition. Now our case. So our group is SL2C. Our three manifold is an ideal tetrahedron. Then its boundary is just a boundary of an ideal tetrahedron. And this allows us to construct the Chern-Simons phase space on the boundary and the Lagrangian submanifold. Okay, great. We have the phase space for Chern-Simons theory on the boundary of an ideal tetrahedron. And it's not enough. We also want to add one more ingredient. So we add a so-called framing flag. I denote it by S, to each cusp boundary of the ideal tetrahedron. I remind you what is the cusp boundary. Let me just copy this ideal tetrahedron to here. And the cusp boundary are the truncated triangle I color in gray here. And what is the framing flag? Now it's a multi-line space of flat SL2C connection. So I can construct holonomy, SL2C holonomy. So now I construct around each cusp boundary, I can construct a holonomy around the cusp boundary, which takes a value of SL2C. And for this holonomy, I can construct what is the eigenvalue, what is the eigenvector. So the eigenvector satisfy this equation, and the framing flag is defined as the eigenvector of this holonomy around the cusp boundary. But up to a complex scaling. So this S takes a value in CP1. Okay? And why do we want to introduce this framing flag? I think I see a question.
Going back to choosing the Lagrangian submanifold,
yeah.
I get that choosing p equals 0 gives us that, and then choosing x for polarization gives us that your momentum operator now becomes our partial of x. But can you motivate that from like maybe a physical or more intuitive standpoint? Can you motivate choosing p equals 0?
Yes, that's another polarization. And I'm just giving you an example of what is Lagrangian submanifold that you see in classical mechanics. Now I generalize this idea, and now I'm not considering polarization. Yeah, it's a generalization concept. Just Lagrangian submanifold as it defined. It's the symplectic form equals 0. The dimension is half of the original symplectic manifold. Okay. So why do we introduce framing flag? Before that, I see another question.
Yes, so can you go back? Let me just make sure. So the point is like this P partial M3 is the phase space of the flat connection, right?
Right.
So it is a symplectic manifold, and then what is this Lagrangian submanifold of P partial M3? It is the manifold of the solution with F equals to 0?
Yeah.
Okay.
In the bulk, yes. Yeah. And I will write you why I will have, how do I realize that F equals 0 soon. So, okay, why do we want to introduce the framing flag? It's because it allows us to define a very convenient coordinate of this phase space. And this coordinate is called the Fourgon coordinate. I will call it FG coordinate. Then this coordinate is for the phase space, Chern-Simons phase space, on the boundary of an ideal triangulation, ideal tetrahedron. And why is it good? Because this coordinate has two nice properties. The first one is that it's gauge invariant. And the second, it has a simple Poisson bracket. Okay, how do we define this using the framing flag? It's the following. So and these coordinates are associated on the edges of the geodesic boundary. For example, this edge here. And we know that each edge on the boundary of the ideal tetrahedron can be viewed as a diagonal of a quadrilateral. For example, I have the quadrilateral like this, and here is the diagonal. Of course, all the vertices, they are truncated vertices, so I should put a gray triangle here. And the FG coordinate is associated to this diagonal edges. I call it X of E. Say this edge is E. And how do we do that? First, because we introduce a framing flag to each cusp boundary, say S1, I'll put a prime, S2 prime, S4 prime, S3 prime. First thing to do is to parallel transport them to a common point. I would define the Si equals to Hi, which is the holonomy, Si prime, for I equals to 1 to 4, because I have 4 cusp boundary. And let's choose a point inside this quadrilateral, and I parallel S1 prime using H1, parallel transport S2 prime using H2, and then H3, H4. And then I define the S1, S2, S3, S4. Then I can now, using these parallel transported spring flag, I define the FG coordinate in this way as a cross ratio, which is S1, S2, S3, S4 over, in the denominator, I exchange S3 and S2. And what is this inner product? Because the framing flag is an eigenvector of the holonomy, in the fundamental representation, I can write it as two components, S0, S1, which is in, I told you, it's in CP1. So it's also in a subset of two, it's represented by two complex variable. And this inner product for xi, xj is defined as S0, Si0, Sj1 minus Si1, Sj0. Then you immediately realize that Si cross Sj, this is anti-symmetric. And this inner product has a nice property. It's gauge invariant. So Si wedge Sj is equals to I parallel transported Si with G and parallel transport Sj also with G. Then they are the same for any G in SL2C. So if I use this inner product to define a coordinate, of course it's gauge invariant. So we see the first nice property. And second, what is a simple Poisson bracket? So first I take the logarithmic of this coordinate. I denote it as e to the chi e. Then this chi e has very simple Poisson bracket. Suppose I have chi, e and e prime associated to different edges. Then it has three possible results. First, it's equals to 1 if e is on the left of e prime. Of course, the vertex is also the cusp boundary. And it equals to -1 if it's the opposite. And equals to 0 if this e and e prime, they are not connected to the same cusp boundary. It's very simple. So we see the nice property of this kind of coordinate. Now, how many coordinates do you have on the boundary of an ideal tetrahedron? Now, on ideal trigon, on the boundary of an ideal tetrahedron, I have 6 edges. I told you that these coordinates are associated on the edges of the boundary of an ideal tetrahedron. But because it's a moduli space of flat connection, so we require the eigenvalue for the holonomy around each cusp has to be trivial. So I have lambda equals to 1 for all the cusp boundary. I have 4 of them. So you immediately realize that the dimension of this phase space has to be 2. Question?
I got a little lost when you labeled the geodesic boundary chi e, and then so this inner product that you give by introducing the flags will be a number. So should I think of chi e as perhaps the length of the geodesic boundary?
No, it's not a number, it's a variable. It's actually a function of the connection, which I will just tell you in a minute.
Okay, thank you.
So we immediately know that the dimension is 2.
So what is this S prime?
S prime, it's a framing flag I introduced at the cusp boundary. It's the eigenvector of the holonomy around that cusp boundary.
So this is the reason. So could I understand like this X prime because it is the eigenvalue, or eigenvector. So it characterizes the holonomy at each.
Yes.
And the holonomy is the phase space.
Holonomy, it's a function of the phase space variable.
So that means like this S prime is like the coordinate of the phase space.
It's a function of the coordinate. It's a function on the phase space.
Okay, okay.
Okay, so 2 dimension. So we can find 2 FG coordinates. I would denote it. So okay, the kinematical phase space, and it's spanned by 2 coordinates. I would denote it by Z and Z prime, Z double prime, and they are located on the edges. Let me also copy paste. Let me copy paste again. They are associated to the edges. I would say this is E, and this is E double prime. And you will realize that on the opposite edge, they are associated the same FG coordinate just by direct calculation using the framing flag. And I also introduce a redundant coordinate, I call it Z prime, on the remaining 2 edges. And then I can, using the Z and Z double prime, I can write, because they are phase space coordinates, I can use them to write out the symplectic form. And the symplectic form is dz double prime over the z double prime, wedge dz over dz. And this is actually only the holomorphic part, and we also have the anti-holomorphic part. And it's spanned by z bar. Just take the complex conjugate of them, and I can also write the symplectic form using the z bar double prime and z bar. Sorry, this is z bar. And because we know that holonomy the phase space is a phase space of flat connection. The holonomy is a function of connection. Then if I solve the eigenvector, which is a framing flag, the framing flag also is a function of the connection. Then I use this framing flag to construct the coordinates, which is z and z double prime. So this z and z double prime, they are also a function of the connection. So these symplectic form, they're just represent of the symplectic form that of Chern-Simons theory I introduced in the first lecture. So it's related to this symplectic form. Okay. Here I have z double prime. I said it's redundant because it's a function of z and z double prime. More precisely, equals to -1 z and z double prime. Okay, so it's redundant. Now, if I combine the holomorphic and anti-holomorphic part, then the symplectic form of the Chern-Simons theory. Now I put the complex coupling constant here, then it becomes t over 4 pi omega plus t bar over 4 pi omega bar. And here again, this t and t bar, they are complex coupling constant. Now we have the phase space of the on the boundary of the ideal triangulation or ideal tetrahedron. Then if I require the bulk of the ideal tetrahedron to be flat, then I can also construct the Lagrangian submanifold for the ideal tetrahedron. How do we construct it? We construct it by requiring that it's flat in the bulk, which means that the holonomy, if I construct the holonomy, it must be identity. Then it will be a flat. How do I construct holonomy? We see from here that holonomy is a function of connection, and the coordinates are also a function of connection. So you can get an idea that we must be able to construct a holonomy out of this coordinates. Here's double prime. Why do I put double prime here? Okay, so there's a rigorous way to do that, and this is called the snake rule. But I'm not going to tell you all the details of snake rule. You can refer to the equation 40 in the lecture note. I think it's on page 11, if I remember correctly. But I'll just tell you the result. The result is that this results on the boundary of an ideal tetrahedron. And the holonomy in the fundamental solution is equals to 1 the diagonal is 1, 1 because the eigenvalue is 1 already. And the off-diagonal lower triangular element is 1 over z double prime times z double prime plus z inverse minus 1. And this upper triangular element is 0. This is in SL2C. If I require this to be 1, that just means that this must be 0. So the Lagrangian submanifold, I can write it using the coordinates, the FG coordinate. It is defined as the coordinates, which is z double prime. I also have the complex conjugate part of it, such that it satisfies the z double prime plus z inverse minus 1 equals 0. Also, I have the complex conjugate part. Bar minus 1 equals to 0. And this is the Lagrangian submanifold using the coordinate of the phase space. Okay, now we have the phase space, we have the Lagrangian submanifold. We can quantize it just using the canonical quantization. But wait a minute, we don't know how to quantize it. We're not quite familiar with how to quantize it. What we are really familiar with is something like this in quantum mechanics. So if in quantum mechanics, if you give me a symplectic form, which is some real constant, and I have some coordinates with tpi wedge tqi, where this is a constant is a real, it's a constant, then I know how to quantize it. How to quantize it? I just quantize the q to a multiplication operator, q hat, and the p is quantized to a derivative operator. So h bar c partial qi. Then I know how to quantize it. But here, this is our symplectic form, which is we have dz double prime over z double prime wedge dz over z. So it's not in the same form as what we are familiar with in quantum mechanics. So how to do that? We do that by doing a reparameterization of the coordinates. So what we do is to parameterize this z and z double prime. So we write it as a function of two parameters. One is mu, one is m. And it's defined as exponential of 2 pi I over k, and then minus b mu minus m. And the z double prime is also a function of two parameters, which is nu and n, another two parameter, but in the same form. So 2 pi I over k and minus ib. I will tell you what is b in this form. What is b? This b is a function of the Barberi immersive parameter in this way. B squared equals to 1 minus I gamma over 1 plus I gamma. And you realize that you can calculate, you realize the real part of the b is larger than 0, and the imaginary part of b is non-zero. You also realize that the b, if I take the complex conjugate, it gives me b inverse, which means that b is just a phase factor. It must be able to be written in this way. Okay, this is a parameterization of z. I can do the same thing for z bar, just to do the complex conjugate of it. Then you realize that I just should change z bar, change b to b inverse, because b bar equals b inverse, and then change minus m to plus m. And here is the same thing. Now, which space does this parameter mu, nu, mn take? This mu and nu, they are real number. They are real variable. And m and n, they are discrete variable, and they take integer up to modulo k, which means that this m and n, they can be taken, if I choose the branch well, then it takes value from 0, 1, 2, up to k minus 1, where k, I take it to be a positive integer, just for simplicity. So already from here, you already get a sense that we will get some truncation for this discrete variable. And this will lead us to the finite amplitude in the end, which we will see tomorrow. Okay, and now I can rewrite, using this new parameter, I rewrite this symplectic form for the Chern-Simons theory, which gives us 2 pi over k, and then d nu wedge d mu minus dn wedge dm, from which I can derive the Poisson bracket of the new parameter, mu nu equals to Poisson bracket of nm equals to k over 2 pi. Now we're happy, because this is the form that we are familiar with in quantum mechanics. So we can know how to quantize it. Let's quantize it. So the next thing to do is to do the quantization of the Chern-Simons theory on an ideal tetrahedron. So to quantize it, we introduce a quantum parameter. Which I denote by Q.
Excuse me?
Yes.
So question here. So here you see this m and n, they are just like integer.
Yes.
And then how do you define this dn wedge dm?
The dn wedge dm?
Yes,
we get it.
because if m n they are integer, so it is not like R4. Yes, R4. And then how do you have this dn wedge dm?
No, we just derive directly from here. I just write it in, I express z and z double prime in terms of mu m and nu n. Then I just get the result.
So that means like this m n, they are also real number, right?
No, they're discrete number. Or you can think of this d as a jump. But I have the dn over k. If I take the k large, then it's more like continuous, but it's discrete. Okay, let's quantize it. We quantize it first by introducing quantum parameter q, which is exponential of another parameter h, and q tilde another quantum parameter, or exponential e to the h tilde. And this h is a function of the complex coupling constant. It's equals to 4 pi I over t, or it's equals to 2 pi over k, 1 plus b squared. And this h tilde is just to replace the t by t bar, or another way is to replace the b by b inverse, so b minus 2. And first thing first, why is it called quantum parameter? Because we know that the k, if you remember, it equals to 12 pi over gamma Planck length squared absolute lambda. We know the quantum parameter is the Planck length, which is a function of the h bar, the Planck constant. And when this goes to and we know that this now then h and h tilde, they are also function of the k, then it's also a function of h bar. That's why they can be viewed as a quantum parameter. And if I take the scale which is much larger than the Planck's length, or I take the Planck length to 0, then this is the classical limit. And this classical limit can be also represented by taking the k to a very large, or equivalently, the h goes to a very small number, or the q and q tilde, they are very close to 1, and this is a classical limit of this quantum parameter. Now, we can just do, as in usual canonical quantization, we quantize the Poisson bracket, which is the Poisson bracket of the coordinate mu, nu, m, n here, to a commutator of operator, which I put a hat here for the quantization, and this gives us k over 2 pi I. This is the commutator of the quantum operator after we do the quantization. And also, at a classical level, we have the kinematical phase space, which is P partial ideal tetrahedron. And this is quantized to the kinematical Hilbert space. What Hilbert space should it be? I would denote it by H kinematical, because we have the continuous parameter mu and discrete parameter m. So very naturally, the kinematical Hilbert space is the square integrable function on a real number, and V4, or this Vk. This is just the k-dimensional complex plane, because we have the discrete variable m which can take the value from 0 to k minus 1. And this is because we have a parameter mu here. And also, this Hilbert space has an inner product. We just define the inner product for any function f or g, which is defined as the integral for the parameter mu, and the sum for the m, which takes a value in z mod k, and for any function, which is a function of mu and m now, and another function g of mu and m. And they are function in the kinematical Hilbert space. And this is the inner product associated to this Hilbert space. And also, we quantize the operator to multiplication operator and derivative operator that we are very familiar with. So this mu hat, they act on a function in the Hilbert space as a multiplication operator. Then the nu hat, which is the complex conjugate, it's a conjugate momentum of the mu. It will just quantize. It's just quantized to the derivative operator. So it's equals to minus k over 2 pi I partial mu of this function in this Hilbert space. And mu and m and n are similar, but they're discrete. So we, instead of writing as the derivative operator, we'll write as a shift operator. So we write in a slightly different way. For the m, 2 pi o to e to the 2 pi I over k, m hat, it acts on the function of the Hilbert space as a multiplication operator. And the n hat acts on the same function by shifting this m by 1. So that's how they act on functions of Hilbert space. Then I can also construct this z before we do the parameterization. Then it's the operator of it, just to put a hat on its parameter we see in the classical. And z double prime hat is equals to exponential 2 pi I over k minus ib nu hat minus n hat. So using this, you can also write how they act on a function. And z act on a function, which is a function of mu and m, or I can write it as a function of z and z bar. They are just the same thing. And this is a multiplication operator again. And the z double prime hat, it acts on this function by multiplying the variable z with a q. And for the z bar part, I also the operator is also a multiplication operator. And the z bar double prime, it multiplies the variable z bar by q tilde. So it's a very simple operation on the function of the Hilbert space, kinematical Hilbert space. Now, also, classical level, we have the Lagrange submanifold. And this can be also quantized because the Lagrange submanifold is described by restricting the coordinate to satisfy a constraint. This constraint, after quantization, they become a constraint operator. So this is quantized to a distribution that satisfies the following operator. This operator is nothing but a z double prime hat plus z minus 1 hat minus 1. and it acts on a function which is a function of z bar equals 0. And we also have the bar version of it. Then we'll just try to solve it. And the solution is given by it's called the quantum dilogarithm function. And it's written in the following way. So I denote it by psi triangle, which is a function of mu m, as usual. And it includes an infinite product from j equals 0 to infinity, and 1 minus q tilde to j plus 1 power, and z bar inverse over 1 minus q to the minus j, and z inverse. And first thing first, why is it called quantum dilogarithm function? It's because if we take the classical limit, which is q tilde goes to 1, then you realize that this function can be expressed in terms of the dilogarithm function in the following way. It equals to approach to the, let me just write equal, minus ik over 2 pi 1 plus b squared, and the dilogarithm function of z inverse minus ik over 2 pi 1 plus b inverse minus 2, and dilogarithm function of z bar inverse. And then this is the leading order. I will also have some subleading order. Okay, and this dilogarithm function is defined as an infinite sum n from 1 to infinity to z to n over n squared. And this is defined for z whose norm is less than 1. And if you're still not familiar with what is dilogarithm function, you must know what is logarithm function. A logarithm function is if I do the Taylor expansion around 1, then I get 1 minus z. It's equals to n equals to 1 to infinity sum, and zn to n. And this, again, for z whose norm is less than 1. Then now you see, this is just an analog of the logarithm function by changing this n to n squared in the power, in the denominator. That's why it's called dilogarithm function. And the quantum dilogarithm, because we recovered the logarithm function in the classical limit, so we call this function the quantum dilogarithm function. Okay, so in literature, it's found that this quantum dilogarithm function can be interpreted as some 6J symbol. And this 6J symbol is not the one of SU2 that many people could be familiar with, but it's a 6J symbol of Weyl algebra. And this is related to the Borel subalgebra, the representation of the Borel subalgebra of UQSL2C. And here, the UQSL2C is a quantum group. And this is discovered by the Kashayev in 1994. So there's some similarity, although it's not the 6J symbol that we're familiar with, there's some similarity with the 6J symbol of SU2. First, it's the quantum state of an ideal tetrahedron, and the 6J symbol of SU2 is the quantum state for a tetrahedron. This is the first similarity. And second similarity, if you're familiar with the 6J symbol and how to derive it, you know that it is derived by a recursion relation. And this quantum dilogarithm function can also be derived using, from a recursion relation. And this is just what we wrote here, because I've told you that z double hat act on the function. It just multiply the variable in the function by q. And because of this equation, I know that it must be equals to 1 minus z to the inverse times the function. And we also have the bar version of it. And it multiply the variable Z bar by Q tilde. And this gives us another recursion relation. And using this recursion relation, you can actually derive what we got here. So this is another similarity. Great. Now we get the quantum logarithm function for an ideal tetrahedron. And this is nothing but this function of mu m. This is nothing but the potential function of an ideal tetrahedron. And as I told you at the end of last lecture, using this potential function, I can eventually construct the potential function of the gamma 5 graph complement of a 3-sphere, which will lead us to the spinfor model of 4D quantum gravity with a non-zero lambda. Okay, so now we have our building block. Since it's so important, let me also tell you some property of this quantum logarithm function. So first, this function, it has a singularity at mu z equal to 0, which is bad, because if I do the integration over this function, it might give us some divergence. So how do we do that? The way to solve this problem is to do the analytic continuation. So we perform the analytic continuation of the variable mu. So I let it to take the value in complex variable. Then its conjugate momentum, nu, must also take a complex variable. Then if I do an integration of the quantum logarithm function, then I can, if d mu, instead of integrating over a real line, I can shift it by introducing a imaginary part. Then now it's this function, which is a function of mu m, it's now a function of a complex variable mu. And this turns out to be a meromorphic function. Of the variable mu. And in particular, it turns out to be holomorphic in the upper plane of the mu. So that when the imaginary mu is positive, and it has poles only in the on the real line and in the low half plane. And if I draw the location of where the poles are, then I have axis real mu, imaginary mu, and the poles are at the origin, and then this is how the poles are located. It's like this pattern, and go on. So this means that I can just shift the integration of contour if I want to do the integration over this function by, instead of, here's the real line, instead of integrating along the real line, I can shift it above. Say this is the distance is alpha, and this becomes a new integration of contour. And actually, I introduce the imaginary part. I just fix the imaginary part, and I call the imaginary part of mu equals to alpha, imaginary part of nu equals to, it's a beta, I denote it in this way. And as long as I can make sure that this imaginary part, they satisfy some condition, I call it P. This is called the positive angle structure. And this positive angle structure just structure so to lead us to a convergent result after we do the integration. I don't have time to dig into detail, so I will just refer you to the lecture note in page 14 to 15 if you're interested. Okay? And that's it. And so I'm just telling you the property of it. How much time do I have left? 4 minutes. Then let's do a 4 minutes exercise. So let's do an exercise. Now I have 20 ideal tetrahedron. I want to glue them together to form the boundary of the gamma 5 graph complement of a 3-sphere. And let's first glue 4 ideal tetrahedra together. And they would form a octahedron. And I was very clever to secretly store this here, so that I don't need to draw again. And then make it bigger. This is an ideal octahedron. I glued 4 ideal tetrahedra together, and here, one of them is this. Here's the cusp boundary, and another cusp boundary, another cusp boundary, another cusp boundary on the bottom. And I have 6 edges, 1, 2, 3, 4, and 1 that's already in red. This is 1 ideal tetrahedron, and I glue 4 of them together in this way. And now, and this is called the ideal octahedron. I denote it by oct. And because now you see that this link, this edge, is in the bulk of the ideal octahedron, and because we are working on a flat connection of a 3-manifold, so it must be flat in the bulk. So this means that there must be some constraint associated to this link. And eventually, if I associate the coordinate, if I say this is x and y, z, w, because I have 4 ideal tetrahedron, and the opposite edge is also associated to x, y, z, w. And the mechanism of it is just to product them together. Then my gluing constraint turns out to be x, y, z, w equals to 1. And I will also have the bar version, the complex conjugate version of it. But since I analytic continue the mu to be a complex number, so the z bar, if I define in the same way as before, it's no longer the complex conjugate of z. So I would call them, instead of z bar, I would call it z tilde, also for the x, y, and w. And this is another constraint. This is a gluing constraint. Then the phase space of the boundary of the ideal octahedron, it becomes a product, the direct product of 4 phase space of ideal tetrahedra, product them together, but quotient, double quotient by the constraint c and c tilde here. So it's actually smaller. Then if I take the exponent, the logarithm of these coordinates, s equals to x e to capital X, y e equals to e to the capital Y, and so on, then my coordinate of the ideal octahedron becomes, it was originally, so this constraint allows us to write the w as a function of x, y, z. So the dimension of this phase space is 6, because it's the dimension of this equals to 2 times 4, and then minus 2 because I have 2 constraints. Then it becomes 6. And the logarithmic coordinate, I would denote it by x, y, and z. And the conjugate momentum, I denote it by px, py, and pz. And you can also write out what is the symplectic form, and then you can write out what is the Poisson bracket of it. And I think more details, you can find it in the lecture note, but I will tell you why I introduce it, because we use it. This structure appears in the ideal triangulation of the 3-manifold that we are interested in. And this can gives us the partition function of an ideal octahedron, which is a function of x, y, z, and px, py, pz. And it's just the product of the ideal of the partition of the quantum dilogarithm function, which is function z tilde, and then y tilde, and then I will have function of w, which is a function of x, y, z now, and function of x, y, z, and p, x, y, p, z, actually. And then w tilde is also a function of them. And this is the partition function of an ideal octagon. And we will continue tomorrow.